Hello friends, so welcome again to my channel. So today we are going to discuss message queues, asynchronous communication between services. So if you are new, then it's a high level design series. So we already discussed a lot of topics and you can find these topics by my previous videos, or if you want a quick check, then I always upload all the topics here, like all the details, right? So just like as today's. So if you go here, HLD, so I will share the link. Then you're gonna see all the data here and then building blocks, all the data here. So I already prepared some data for message queues as well for your reference purpose, right? You can go to my videos again and again as well to have a better idea, right? So if you're new, then subscribe the channel because uh, I gonna have other multiple topics as well. So these are building blocks and trade-offs are very, very important, right? Trade-offs are very important, and then we're gonna have LLD as well. So these are kind of conceptual, right? These are conceptual. You can see and you can learn, right? But these are very important, right? We gonna write code practice as well. We're gonna do coding practice as well here in LLD sources, right? Meaning, what does it means? Oops, simple, right? Solid. So here we're gonna write code for each and every principle, right? Then patterns. We're gonna write each and every code for patterns, right? Load of right. And again, we're gonna have other problems as well, just like as simple state machine diagram. Sorry, this is also a kind of a pattern. So we're gonna have multiple examples as well, right? Just like as car parking lot and like gaming thing, right? So all these we will cover like examples as well. Just like as if I can see, uh, okay, so here I don't have examples given, but the thing is, whenever we will done with all these things, then we'll switch to examples as well, and we're gonna write real. I will write a real coding right in front of like you, meaning we'll do all together, right? So this is a simple like we gonna do like everything step by step, right? So right now today's topic is message queues, and without wasting of time, let's get started. So I will paste the link of these details as well in the description. Okay. So what is message queue? So you already know, right? Uh, okay. We have two types of communication: sync communication and AC communication, right? So when we create a async channel, right, then we need some sort of interface, right? So that interface is called message queues. Understand with the example. Suppose we have some shopping website, right? And over there we have some order service. Okay. And order service communicable. So I already write example here as well, but I wanna explain, right? Order service and then payment service and then inventory service and then shipping service. Okay. So the thing is order service, payment service, order service, inventory service. Let's say like this: order service, shipping service. Okay. So all these services are independent to order service. Inventory meaning we gonna these are not like these are tightly coupled as well or non tightly coupled as well. But these are not dependent actually. The word is dependent, right? Order service, payment service. So after that we have to manage inventory as well, right? So we can manage this anytime, right? Not dependent on order, right? Shipping service. We can manage this service later as well, right? Not dependent. Thing is, if we create structure like this, if we make a dependency, right? Order service, then payment, then inventory, then shipping service, tightly coupled, right? Everything dependent on previous service, then it will be tightly coupled, right? If we create some sort of channel in between, meaning order service, then we have channel, here we have channel, then inventory service, Then we have channel, then we have shipping service. So if you create channels and then data will get sent to here, or might be a single channel, not a three channel, or we can say only a single channel. Okay. So it send data to this channel, and then they are reading the data from here. They are reading data from here. They are polling data from here. The word is poll. Okay. So polling and working accordingly. Okay. So in the technical term, this is term as producer. This is a Kafka or message queue or RabbitMQ, whatever, and these are consumers. Okay. So we'll discuss. We will deep dive as well. So I wrote here. So this is the this one was async. Okay, this one was async, like tightly coupled. Every service depend on each other. This diagram was for async. This was sync. Right. This is not dependent. Right. Order is not dependent on payment. Order is not dependent on IS inventory. Order not dependent on, meaning inventory is not dependent on order. Payment is not dependent on order. Like this. Okay. So now sync service. So why we need this? Why we need this message queue? Okay, this is a important thing. First of all, every step wait for previous one to finish. Right? It will get finished, then it will get finished, then response will go to here. It will get finished. Meaning these four services will wait for this whole time. Suppose every service taking like 10 seconds, then shipping service will gonna take like delay for 40 seconds. Right? So tight coupling. This is the issue. Cascading failure. Suppose inventory service is down, right? Then it will wait for the service, right? Doesn't make sense, right? So cascading failures. No load buffering in a spike, right? Suppose our system is able to handle only 10 million requests, right? 10 million requests. On Black Friday, we we get 1 billion requests in one go. 1 billion requests in one go. Then what will happen? 90 million get piled up. 90 million requests get piled up. And after timeout, it will get lost or might be retry failure, something like that, right? So no load buffering, latency stack. No, the customer wait for the sum of all these five first. Sorry, customer ordered here, right? At step one, customer order here. Customer waited for 10, 20, 30, 40, 50 seconds to get message. Your order is shipped, right? So this is the kind of a latency stacking. Now the fix is decouple producer and consumer in time space manner, right? So whatever I explained here, right? The same thing. Order, message queue, payment service, this and that, right? So in that way, it can work in parallelism as well. Payment service can fetch data from Kafka or message queue. Inventory service from this message queue. This is like from this layer, right? Kafka. These all can work all together, or whatever it was taking 10 seconds. So 10 seconds it will process the whole order, right? Parallel rhythm. Okay. So now core concept and terminology. So let me drop a very good diagram kind of thing for a user. Then we're gonna have a message queue. Then we're gonna have, I can say message queue, Kafka or RabbitMQ. I'm good in Kafka, so I can explain Kafka things. Then we're gonna have, I can say, uh, broker. Then we're gonna have topic. Then we're gonna have partition. Okay. So broker one, broker two, but sorry, topic one, topic two, Then we're going to have partition 1, partition 2, partition 3. Okay. Then we're going to have offset 1, 2, 3, 4, 5. Offset. Okay. Then we're going to have consumer group. Consumer group 1, consumer group 2, CG1, CG2. Then we're going to have consumer 1, consumer 2. Okay. So these are kind of high-level diagram of our messaging queues. Okay. So producer is kind of a client who sends the data to message queue or Kafka or RabbitMQ, whatever, right? So message queue, and then underneath we have brokers. So I'm just taking example of Kafka because Kafka is very famous nowadays. So Kafka is nothing but a server, right? Under we have multiple brokers. I can say we can say Kafka cluster as well, right? So under we have broker 1, broker 2. Okay, broker 1, broker 2. So under broker we have partition 1. Sorry, topic 1, topic 1, topic 2. So under topic we have partitions, partition 1, 2, 3, multiple partitions, right? And under partition, not partition, partition divided into offsets, right? So I will explain each and every step, each and everything, right? And then here's consumer group. So all the consumer group subscribe to topic. Okay, so now consumer group subscribe to topic, not cluster, to topic, not broker, to particular topic. Okay, then under consumer group we have multiple consumers. So now we have 1, 2, 3 partitions here. Suppose CG1 subscribe to topic 1. Okay, now in topic 1 we have 3 partitions, partition 1, 2, 3. Okay, so say here we have 2 consumers. So when it loads up partition 1, this binding will go in the starting, right? So now we have 2 partitions. Sorry, we'll go C1, 1 partition P3 will go to C2. Because binding will go in will bind in certain. Okay. Suppose in future if we add consumer 3 in CG1, then it will automatically refresh and it will break one partition, right? And it will assign partition 1 to consumer 3. Okay. So this is a high level structure. Now let's understand the terminology. Okay. So offset, you're gonna say offset. I left with offset. So partition. Suppose P1, P0 is coupled by C1, right? So it has 1, 2, 3, 4. So this is a partition. These are offset number. Offset, 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 offset. Okay. What happened? It will consume. So kind of index, right? Index 1 is like offset, right? So suppose C1 consumes offset 1, then offset commit. After consuming, it will say whenever consumer consume message 1, it will say offset commit, it's done, right? Then consumer 1 again consumes message 2, again it will does offset commit, it is done, done, done. Okay, so these offsets are used for tracking the messages. Okay, suppose consumer is down somehow, consumer 1 is down, so 3, 4 are uncommitted, right? So these are still, so might be partition 0 will assign to consumer 2, or it will wait until this up. Any case, right? Suppose C1 get up in couple of seconds, then it will poll. So polling like Kafka handles everything. So consumer will poll the message again, like it will get the message 3. How it will get the message 3? Because internally it saves the offset number, right? So it will see this is unread, number 3 is unread, so it will send the third message to the consumer. Okay, so this is a terminology for offset, right? Now acknowledgement. So this offset commit was acknowledgement. Offset commit was acknowledgement. Okay, so producer service the publish a message, like this is a publisher, sorry, producer, consumer which consumes the message, broker, now broker, topic, partition, consumer group, offset, acknowledge. Okay, so everything. So two types of model we have: point to point and publisher subscribe model. So what does point to point means? One message exactly one consumer. One message exactly one consumer. Okay, used for task distribution, process the message, sending an email, whatever, right? So SQS traditional MQ have this thing, right? So I told you, I gave the example of Kafka. Okay, so Kafka is a PubSub model. Okay, so let's discuss this point to point first. So producer will send the message to queue, then it will gonna have two partitions. Then we gonna have consumer A will read from message one, consumer two pick up the message two, right? Again, point to point, message one exactly one consumer. Okay, now what does it means? Exactly one consumer meaning uh, this topic one can be subscribed by CG2 as well, consumer 2 as well. Okay, might be third party as well, third party consumer groups as well. Okay, so what is going to happen? All the message will go to here, here, and CG1 as well. Okay, so that's why. So multiple consumer, not a one consumer, right? Multiple consumers. So that's why it is a point-to-point model. Now, PubSub model. So what I will explain here, this is a PubSub model. One message, every subscriber get a copy used for event broadcasting. Okay, just like as we discussed earlier, right? Payment, inventory, analytics, whatever. Example, Kafka topic. SNS, RabbitMQ exchange. RabbitMQ exchange, fan out, right? Fan out. So this is an example of fan out, right? This is an example of fan out, meaning publish message to the topic somehow. Suppose one message published, subscriber are four, right? Subscriber one, consumer two, consumer three, consumer four. So the same message one will go to every subscriber or consumer, right? So this is a fan out also. So whatever I was explained earlier, right? Here subscriber ABC, payment, inventory, analytics, right? So this is a kind of publish publisher subscribe model, right? I already explained here, right? Publisher subscriber model. Now delivery semantic, very very important thing, right? You will get, if anybody will ask Kafka, then they will ask delivery semantic as well, right? At most one. So three semantic we have. At most one, message may be lost, never duplicated. At most one meaning the message will go only one time. Fast and forget. It will send one message and then disappear. Go. At least one. At least one time it will so go. It can create duplicate message as well. It may create duplicate message as well because message is never lost, but maybe deliver more than once because now consumer caches after processing, but before committing. Acknowledgement before offset commit, right? I gave example, right? One, two, three. It is at one, consumer poll this message. One, okay. It consumes, but it crashes before. offset, then what gonna happen when it, so it is down, right? When it gonna up, it will get whole again one because no commit was happened, right? So that way it will be duplicated. But again, it depends. So this example I gave you for delivery semantic at least one. So this is the configurable, right? We can configure at most one, at least one, and exactly once, right? So we always, this is a default, this is a default, the default for real-time systems, right? Because otherwise we're gonna lose the message. At most money, very dangerous, right? But it depends on our uh, trade-off, right? It depends on our trade-off. But usually we go with at least one, right? Exactly one means the message processed exactly one time. No duplicate, no loss. Okay. But but now you will say it is a very good. Why we are not going with this? So just see this. Extremely expensive to achieve. Extremely expensive to achieve end to end. Okay, requires distributed transactions or carefully data plus independent writes. Okay, so what it means? Kafka offers exactly one semantic within its own ecosystem. Producer, topic, consumer, using traditional APIs. But soon you can cross external APIs, the calling third-party payment API, the third party, sorry, exactly one is effective, impossible to guarantee. Meaning, I told you here, right? We have multiple subscribers, multiple subscribers. Okay, multiple subscribers. What will gonna happen? We have, so now we have exactly one policy, right? So in exactly one policy, if this is a one system, then we can manage, okay, by using our internally idempotency key, by managing idempotency key. But the thing is, if you have external subscriber one, external subscriber two, right? So it doesn't know the keys, right? In that case, it is hard to manage. So we need to send the key to external guys as well. So this is internal we can manage, but this is the hard. So this is the way it says internally it can manage easily, but when we're gonna have external service like subscriber, then it will be a little bit difficult, right? That's why exactly once we go with now scaling thing. Uh, when you ask how do you do guaranteed exactly once, how you do guaranteed exactly once, the question was, sorry, when interview asks how you do guarantee exactly once, then the answer is I design at least once. Whatever I was saying, delivery with consumer idempotent. With consumer idempotent. That's the pragmatic, provable, correct approach use a scale. Okay, so usually this we always use in our production as well. Meaning key value, right? Key value. When we publish message, we always, not always, for maintaining exactly one thing, we're going to send key, identity key as well. It will treat as a identity key. Then subscriber, you know, like identity, right? Subscriber, it process key one, okay, right? Key two, key three. If it processed key one, right, it is done. And if it receives the same message again with key one, right, it will ignore because this key is already done. So this is a kind of identity thing, and this way we're gonna handle exactly once uh, semantic, right? How Kafka achieve scale? Simple. In partitioning, a topic order event is split into say 12 partitions. Okay. Producer hash a key to decide which partition message lands in. I told already, right? Um, so I'm not sure I told her or not. So when we have multiple partitions, partition 1, partition 2, partition 3, producer, right? So Kafka do hashing, right? Kafka do hashing, then accordingly it sends data to partitions. Okay. Now we can increase the partitions, right? Simple. We were talking about scaling, so we can increase partitions, and when can scale out for consumer group, we can scale out consumer groups, right? So if you have a consumer group with 4 consumers reading order event like 12 partitions, Kafka assign 3 partitions to each consumer and scale the group to 12 consumer and get exactly 1 partition. Meaning, I think you already understand, but still, if you don't get topic, I think I already explained before as well. Topic 1 has, let me check. Yes, this thing I already explained, right? So starting we had only, let me quickly explain as well. Starting we have partition 1, partition 2 only. If we are only one consumer, later, so little bit load, right? It will read the message from this and then from this, but and we decided to increase the partitions, right? P5, and we so every partition will go here, more load, right? So in future we added multiple consumers as well to scale our structure, right? So P2, P5 will go here like this, like this, like this, like this. Okay. So in this way we can scale our architecture, right? Replication. So we can replicate the brokers. Let's see. Each partition is replicated across brokers, commonly factor of 3, with one broker as a leader, handle read write, other as follower. If the leader broker dies, follower is prompted. How the Kafka achieves durability and availability. I explained this already, right? So multiple brokers, right? Already I wrote 2 because I know like it will be better to write 2 before for scaling purpose, right? So this becomes a leader, suppose, and another broker will become a follower. If it fails down, then it become a leader. If we have other broker, then that will be follower, right? So in this way we can add brokers, then we can add multiple whatever the internal we have here, right? So in this way we can scale this out. Okay. Now retention and deletion. Unlike a traditional queue, message deleted after acknowledge, right? But Kafka retain for a 7-day, or we can increase the window as well, right? Retention and retention or deletion. So we are talking about especially for Kafka. Okay. Now handling failures. Retry, DLQ, poison messages. Retry with Backoff. If a consumer fails, process a message, don't retry instantly. Hammer. Okay, so what does it means? First of all, right? Uh, in Backoff, we give seconds and time. Time meaning number of iteration, right? 2 seconds, iterations are 3. So Kafka internally handle the retry. Kafka internally handle the retry, right? After 2 seconds, it will retry. Just like as um, while retry is less than 3, something like that. Okay, it will process after 2 seconds. So that dot sleep is 2 seconds, something like that. So it will retry after 2 seconds, 2 seconds, 2 seconds. This is the same retry with Backoff. Okay, so dead letter queue. It's a kind of a connected topic as well. Suppose we called retry method, right? It call this procedure, right? Procedure meaning internal coding, right? Backoff or something, whatever, right? So, but again, we called retry, it returns, okay. Let's say it has a boolean meaning successful or not. So we get, suppose we get here not successful, right? Not successful. We get not successful here. So what we gonna do? What we gonna do? Let me go like this. Suppose why I'm not able to select. Okay. Sometime it happens, you know. Oh, looks like it's a bug. Uh, Not able to select. Not sure why it is not going away. It's wasting our time. Okay. So somehow not sure what was the issue, but now I'm able to surf that. Okay. So here I was saying if retry, if retry uh, give me failure, right? Failure after three retry, it give me fail or failure, right? Then what I will gonna do? I told you, right? Suppose it has a boolean, and if I get false or something, right? Then I will gonna call DLQ. This is again a separate queue, meaning separate topic. It's a topic DLQ. Okay. Then I will gonna store this failed message. I will treat it as a failed message in my DLQ. Whatever the failed message will be, I will store in a DLQ to store after some time, like to reprocess, or for backup purpose, or I will reiterate later on, right? So dead letter queue. We gonna store our failed message to dead letter queue. Third is visibility timeout, right? Visibility timeout. When consumer pulls a message, it become invisible to other consumers. Okay. Now, if consumer caches before acknowledgement, the message reappears after the timeout, preventing message loss. But this is why at least one delivery exists. If consumer was actually still reprocessing just flow when timeout appears, you can now have duplicate message. Okay. Now, what does it means? Simple. Uh, we can make some sort of timeout, right? If consumer one is reading some message, okay, we're gonna have 30 seconds. If in 30 seconds it will not consume, it will go, right? Then it will be consumed by someone else by using our at least one delivery. Okay. Now let's come to the backpressure and customer lag. Okay. So what it means, customer lag is latest offset in partition minus consumer current offset. What does it means? 1, 2, 3, 4, 5, 6. Okay. Now suppose we have 6 messages. This is offset. This is a partition, right? These are offsets. So now consumer is here. Consumer is at 3. Read. We are currently processing, right? 3 messages left. So total 3 is left. Like total was 6. Like total it was 6. We are reading 3. We are at 3. So 3 are lag point. Okay. 3 are lag point. So or directly we can say, if we have 3 messages, 6 message left, then these are kind of lag point, right? Latest offset minus current offset, meaning latest pointer is 3, kind of pointer offset is, I told you, right? Index, right? Index is 6 minus, we are at 3, 6 minus 3, 3, it's a lag. So scale out consumers, how to get off from this lag? Scale out consumers, batch processing. Now, what is batch processing? Pull and process messages in batch, meaning we have 6 messages, right? 1, 2, 3, 4, 5, 6. So pulling is easy. Suppose we pulled 3 messages altogether. Now this is a batch. Batch message is V1. 1, 2, 3, we again pull this in second batch, right? We process it, then we process it, right? So 3 messages get processed in one go. 3 messages get processed in one go. So this is a batch processing. Back pressure to the producer. Some system says signals up to slow down, harder in PubSub, easier in this and that, synchronous, right? So this is a kind of a back pressure to the producer. What it means? Again, some system signal upstream to slow down. Okay, meaning it generally doesn't happens. But what is trying to say? Producer, Kafka, consumer. Okay, so sometime we are not we are producer. This is upstream, right? This is upstream. It will go down. So this is a back pressure to the producer somehow. Okay. So monitoring consumer lag is one of the most operationally important dashboard in any event driven system. I have flag. This is a key talking point. If asking how do you monitor the system in production? So monitoring customer lag. So everything is customer lag. Everything is customer processing. Okay. Consumer processing. Now, when not to use message queue, a trap for many candidates fail to reach out. This okay. So here I already added use synchronous API, sorry, REST gRPC when a caller needs an immediate response, strong consistency, simple request, debugging simplicity. Okay, when to use REST gRPC. Now, when do you go with queue? Complete later, action complete later, eventual consistency is acceptable. Multiple servers need to react on one event. Producer and consumer scale independently. Okay, so now you are good with this. When to use, when to not use. Okay, so now interview answer. If interview ask, now message queue decouples producer and consumers in time, giving you load buffering, fault isolation, independent scaling at the cost of eventual consistency and added operational complexity. The two big design point to point we discussed, PubSub model for your fan out needs and choosing your delivery semantic. When the practice is almost everyone lands at least once plus redundancy. Okay, because true exactly once across system boundary is not achievable in general case. Okay, we already discussed, right? So it's a summary. Okay, so this was a messaging queue and I explained the structure of Kafka as well. If you have any question, then you can comment on this. Otherwise, this is the full-fledged thing, right? Kafka or message queue. Okay. So for this topic, I'm closing this video now. And again, if you're new, then subscribe the channel. So message queue is done. We're gonna discuss WebSocket in detail in next video. Okay. And for timing, thanks so much and have a good day. Bye.